Hello all. By now, you all will be familiar with the structure of nephron, juxtaglomerular apparatus, etc. And so now we will see how urine is formed. So the first step in urine formation is glomerular filtration, and we will see in detail what glomerular filtration is. Now let's see what is glomerular filtration. As the blood passes through the glomerular capillaries, the plasma will be filtered into the Bowman space through this glomerular capsular filtering membrane. And during this process, most of the components of the plasma except the proteins will be filtered, and hence it is called ultrafiltration. And the product of filtration is called glomerular filtrate. While this filtrate goes down the tubule, it undergoes various changes both in quality as well as quantity, and thus its composition will be altered, and finally it will form the urine. In general, the factors that impair the filtration decrease urine formation, and the factors that facilitate the filtration increase urine formation. Therefore, the determination of glomerular filtration is an important test in the assessment of kidney functions. While the filtrate passes down the tubular portion of the nephron, many substances like glucose, water, electrolytes, etc. will be reabsorbed from the tubular fluid back into the circulation through peritubular capillaries. And this process is called tubular reabsorption. Likewise, certain substances like ammonia, urea, para-aminohippuric acid, etc. will be secreted into the tubular fluid, and this process is called tubular secretion. Thus, formation of urine occurs in three steps. First one is the ultrafiltration of plasma through renal corpuscle, then the tubular reabsorption of water and solutes from the tubular fluid, and third, that is the secretion of selected solutes into the tubular fluid. So as a result of these three processes, urine is finally excreted out. Now, the mechanism of glomerular filtration. This glomerular filtration occurs through glomerular capsular filtration barrier, which we have already studied in the earlier class. So this barrier consists of capillary endothelial cells, basement membrane, and podocytes of the epithelial cells of Bowman's capsule. And this filtration is governed by two major factors: the pressure gradient across the glomerular capillary wall and the filtration coefficient. So now let's see what these are. Pressure gradients. All the pressures involved in determination of filtration are called Starling forces of filtration. Here in the glomerular filtration, the pressures involved are hydrostatic pressures and oncotic pressures. And the Starling hypothesis states that the net filtration through capillary membrane is proportional to the difference between hydrostatic pressure gradient and oncotic pressure gradient across the filtering membrane. So let's see one by one what these pressures are. Hydrostatic pressures. You know what hydrostatic pressure is? It is the pressure exerted by the fluid at equilibrium due to the effect of gravity. So here the hydrostatic pressures involved are hydrostatic pressure in the glomerular capillary and hydrostatic pressure in the Bowman's capsule. Let's see the hydrostatic pressure in glomerular capillary first. It's also known as glomerular capillary pressure, which is notated as PGC. So this glomerular capillary pressure is the pressure exerted by blood inside the glomerular capillaries. And when compared to the capillary pressure in other parts of the body, this glomerular capillary pressure is much higher because the afferent arterioles arise directly from the interlobular arteries and they are short and straight. So this glomerular capillary pressure is much higher when compared to the capillary pressure in other parts of the body. And another thing is that this glomerular capillary pressure is the same throughout the glomerular capillary. That is, from the afferent arteriolar end to the efferent arteriolar end, this glomerular capillary pressure is the same, which ranges between 45 to 70 millimeter mercury. And its peculiarity is that this pressure will be pushing outwards from the capillary. This pressure will be acting outwards. So it favors filtration. Next is hydrostatic pressure in Bowman's capsule or capsular pressure, notated as PBC. So this is the pressure exerted by the glomerular filtrate in the Bowman's capsule, and it ranges between 10 to 15 millimeters of mercury. So this hydrostatic pressure in the Bowman's capsule will be acting outwards or pushing outwards the capsule. So it acts in a direction opposite the glomerular hydrostatic pressure. Thus, it opposes the glomerular filtration too. Okay, so we have seen two hydrostatic pressures here. One is the glomerular capillary hydrostatic pressure and the second one is Bowman's capsule hydrostatic pressure. The glomerular capillary pressure will be acting outwards the glomerular capillary, and Bowman's capsular pressure will be acting outwards the Bowman's capsule. Both these hydrostatic pressure act in opposite direction, and the glomerular capillary pressure favors the glomerular filtration, whereas capsular pressure opposes the glomerular filtration. Now the hydrostatic pressure gradient. So it is the difference between the hydrostatic pressures in the glomerular capillaries and Bowman's capsule, which is about 35 millimeters of mercury. Okay, so we can see that this 35 millimeters of mercury will be acting outwards the glomerular capillary. That means it strongly favors the filtration across the entire glomerular capillary membrane, that is from afferent arteriolar end to the efferent arteriolar end. Now let's see the osmotic pressures. The osmotic pressures involved here are the colloidal osmotic pressure in the glomeruli and the colloidal osmotic pressure in the glomerular filtrate. So colloidal osmotic pressure in the glomeruli means it is the pressure exerted by the plasma proteins in the glomerular capillary. And since the proteins are absent in the glomerular filtrate, this colloidal osmotic pressure in the filtrate is actually negligible. First, let's see about the colloidal osmotic pressure in the glomeruli, notated as pi Gc. As the blood passes through the glomerular capillaries, the glomerular filtration proceeds and the plasma proteins are not filtered through this filtering barrier and they remain in the glomerular capillaries itself. These proteins develop the colloidal osmotic pressure. Okay, so this pressure exerted by the plasma proteins in the glomerular capillaries is called colloidal osmotic pressure. So this colloidal osmotic pressure is not uniform in the glomerular capillaries. That is, as the glomerular filtration proceeds, the concentration of proteins increases by the time it reaches the efferent arteriole. So, the pressure exerted by the proteins also increases at the efferent end. See, the pressure exerted by the proteins at the afferent end is about 20 millimeters of mercury, but it becomes about 35 millimeters of mercury by the time it reaches the efferent end of the arteriole, because the proteins cannot pass through the filtering membrane and it will remain in the blood itself. So as the glomerular filtration proceeds, more and more plasma and other components will be filtered, but this plasma proteins will be staying back in the capillaries, and by the time it reaches from the efferent end to the efferent end, concentration of proteins will increase. so that the pressure exerted by these plasma proteins will also increase as it reaches the efferent end. Okay, I hope you understand it. Now, the colloidal osmotic pressure in the glomerular filtrate in the Bowman's capsule, noted as pi BC. So, this should be the pressure exerted by the proteins in the glomerular filtrate. But as there are no proteins in the glomerular filtrate, this pressure is negligible. And if at all, it should have opposed the colloidal osmotic pressure in the glomerular capillaries. That is, both these should be in opposite direction. And another thing I have to ascertain here is that the oncotic pressure or the colloidal osmotic pressure act in a direction opposite the hydrostatic pressure. That is, the colloidal osmotic pressure in the glomerular capillaries will be acting inwards the capillaries, whereas colloidal osmotic pressure in the Bowman's capsule should be acting inwards the capsule. That is, in a direction opposite their respective hydrostatic pressure. Okay. So this osmotic pressure gradient should be the difference between the colloidal osmotic pressure in the glomerular capillary and the colloidal osmotic pressure in the filtrate in the Bowman's capsule. That is pi Gc minus pi Bc. And we have already said that this pi Bc is almost nil or negligible. And hence the pressure gradient at the afferent arteriolar end is about 20 millimeters of mercury, and that at the efferent arteriolar end is about 35 millimeters of mercury. So we can see that this osmotic pressure gradient will be acting towards the lumen of the capillary. See, the osmotic pressure is acting in a direction opposite the hydrostatic pressure, and in the glomerular capillary the hydrostatic pressure will be acting outward and the osmotic pressure will be acting inward. And in the capsule the hydrostatic pressure will be acting outward and the osmotic pressure will be acting inward. So since this osmotic pressure gradient is more in the capillaries, it will be acting in a direction towards the capillary lumen. Okay, that is, it will be acting in a direction towards the lumen of glomerular capillaries opposing the hydrostatic pressure gradient. And this osmotic pressure gradient will be more at the efferent arteriolar end. Now we know that the hydrostatic pressure gradient act in a direction opposite the oncotic pressure gradient. Also, we know that hydrostatic pressure gradient favors the filtration, whereas oncotic pressure gradient opposes the filtration. So, net filtration pressure or effective filtration pressure is the difference between the hydrostatic pressure gradient and oncotic pressure gradient. Or simply we can say that it is the balance between the pressures favoring the filtration and pressures opposing the filtration. So if we look at the afferent arteriolar end, it is about 15 millimeters of mercury, that is outwards. That is from the glomerular capillaries into the Bowman's capsule. So at the afferent arteriolar end, the net filtration pressure is outwards towards the capsule, which is about 15 millimeters of mercury. Whereas at the efferent arteriolar end, the hydrostatic pressure gradient value is 35 millimeters of mercury and the oncotic pressure gradient value is 35 millimeters of mercury, which means that there is no difference at the efferent arteriolar end. So, the net filtration pressure at the efferent end is 0 millimeters of mercury. So, we can see that the net filtration gradient is always from the glomerular capillaries towards the tubule, and it will be higher at the afferent end and it slowly declines to almost nil at the efferent arteriolar end. here the Starling's force of filtration acts. Starling's hypothesis states that the net filtration through capillary membrane is proportional to the hydrostatic pressure difference across the membrane minus oncotic pressure difference. Okay, so that is the net filtration pressure. So far we have been discussing about the pressure gradients that governs the mechanism of glomerular filtration. Another factor which governs the glomerular filtration is filtration coefficient. It is the rate of glomerular filtration expressed in terms of net filtration pressure, which is dependent upon the glomerular capillary wall permeability and effective filtration surface area. We have discussed the factors which decide these capillary wall permeability and surface area in the earlier sessions, like the molecular size, shape, electrostatic charge, etc. decides the capillary wall permeability. See, the positively charged particles can easily pass through the filtering membrane, whereas the negatively charged particles like proteins cannot be easily filtered. Okay, so these factors decide the capillary wall permeability. And mesangial cells are having a role in the surface area. Contraction of mesangial cells reduces the surface area, whereas its relaxation increases the area for filtration. So, these mesangial cell contraction impairs the glomerular filtration rate, whereas the relaxation of these cells facilitates glomerular filtration rate. Now, what is glomerular filtration rate? It is the amount of filtrate found by glomerular filtering membrane of both the kidneys in a given unit of time. Normally, it is about 125 milliliters per minute or 180 liters per day. See, in the picture, you can see that if it is less than 15 milliliter per minute, it indicates kidney failure. And if it's between 15 to 60 milliliters per minute, suggestive of kidney diseases, and the normal value lies between 60 to 120 milliliters per minute or 180 liters per day. Okay. There are many factors which affect the glomerular filtration rate. Let's consider them one by one. First is the renal blood flow. We know that as the blood flow to the kidneys increases, the glomerular filtration rate also increases. So GFR is directly proportional to renal blood flow. The blood supply to both the kidneys is about 1300 milliliters per minute. And here one peculiar characteristic of kidneys is that its ability of auto-regulation. Not only kidneys, the vital organs like brain and heart are also having this mechanism. So auto-regulation is the intrinsic ability of an organ to maintain its own blood flow or to regulate its own blood flow. That is, any variation in the blood pressure in the range of 60 to 180 millimeters of mercury won't affect the blood supply of kidney. It can maintain or regulate its own blood supply. So this mechanism of auto-regulation helps to maintain the glomerular filtration rate in the kidneys. Next is tubular glomerular feedback. Actually, we have discussed this tubular glomerular feedback in the earlier sessions. So tubular glomerular feedback works with negative feedback signals. The macula densa in the dextroglomerular apparatus senses the load of sodium chloride in the tubular fluid. So if the load of sodium chloride in tubular fluid is higher, means the glomerular filtration rate is higher, and so macular densa releases adenosine from the ATP, and this adenosine causes constriction of the afferent arterioles. So when the afferent arterioles constrict, the glomerular filtration rate also decreases. And several factors like thromboxane, prostaglandin E2, etc. are there, which causes a decrease of glomerular filtration rate that by vasoconstriction. And if the concentration of sodium chloride is less, that means the GFR is less, so it releases macular densa senses the condition and releases substances like prostaglandins, bradykinin, and renin. So these prostaglandins and bradykinins causes vasodilation, permitting more and more blood into the kidneys. So they cause vasodilatation of the afferent arterioles, and this renin causes constriction of the efferent arterioles. So this leads to increase in GFR. And as the signals travel from the tubules to the glomerulus, it is called tubuloglomerular feedback. Next is glomerular capillary hydrostatic pressure. This GFR is directly proportional to glomerular capillary pressure. When this pressure increases, the GFR also increases, and when this pressure decreases, the GFR decreases. We have said that this hydrostatic pressure in the glomerular capillary favors the filtration. Then the hydrostatic pressure in Bowman's capsule and colloidal osmotic pressure, they are inversely proportional to GFR that we have discussed earlier. Then the permeability of capillary membrane. Permeability of capillary membrane when increases, the glomerular filtration obviously will increase, and in conditions like hypoxia, intoxication, etc., what happens is that the permeability may abnormally increase. So in such conditions, the plasma proteins also will be filtered and they will be excreted through urine. Okay. Next is the surface area of capillary membrane. So the GFR is directly proportional to surface area. As the surface area of the filtering membrane increases, more amount of filtrate will be formed. Then constriction of afferent arterioles. The constriction of afferent arterioles causes reduction in the blood flow and thereby reduction in the glomerular filtration rate. Constriction of efferent arterioles, actually it initially increases the GFR, but later on long standing it causes reduction in GFR, because initially as there is a vasoconstriction in the efferent arterioles, blood will not be going outwards, so there will be a stagnation of blood in the capillaries. It causes the initial increase in GFR, but when this condition sustains, what happens is that almost all the substances will be filtered from this blood. No more chances of further filtration is there. And since the efferent arterioles are constricted, the outflow is prevented. So there will not be any replacement of fresh blood. So gradually it results in the reduction in GFR. The next factor which affects the glomerular filtration rate is the systemic arterial pressure. As long as the mean BP lies in the range of 60 to 180 millimeters of mercury, it won't affect the renal blood flow or glomerular filtration rate because of its virtue of autoregulatory mechanism. But once it goes beyond 180 millimeters of mercury or below 60 millimeters of mercury, the renal blood flow will be affected and thereby GFR2. Then sympathetic stimulation. Mild or moderate stimulation of sympathetic nerves will not cause any significant change in glomerular filtration rate. Whereas a strong sympathetic stimulation causes vasoconstriction by the release of noradrenaline, specifically on efferent arterioles. Then the contraction of glomerular mesangial cells. Earlier we have discussed it. The mesangial cell contraction will result in the reduction in the surface area of filtration membrane, thereby reducing glomerular filtration rate. Next is the role of hormonal and other secretory substances. They will alter the GFR by altering the renal blood flow. So substances like ANP, BNP, dopamine, etc. cause an increase in GFR by vasodilatation, whereas noradrenaline, angiotensin 2, etc. causes a decrease in GFR by vasoconstriction. There are various conditions that alter the glomerular filtration rate, can be physiological as well as pathological. Some of them are: one, exercise. In exercise, the GFR is reduced due to sympathetic stimulation. Then pregnancy. As there is increase in the blood volume, cardiac output, etc., the renal blood flow as well as glomerular filtration rate increase. Then posture. Prolonged standing will lead to pooling of blood in the lower limbs, leading to reduced GFR, and a supine posture increases glomerular filtration rate. Sleep. Usually in sleep, due to the decreased circulatory activity, glomerular filtration rate is less. Weather. In summer, the filtration rate is less, whereas in winter or rainy season, it is more. Because in summer, much water will be lost from the body, and hence the ECF volume will be reduced, and thus the glomerular filtration rate too. But in winter, this water loss is less, and hence the ECF volume also is not much altered, thereby GFR not affected much. Gender. As the blood volume for females is less when compared to males, glomerular filtration rate is less in females. Age. As the age advances, the number of functional nephrons decreases, and hence glomerular filtration rate decreases with advance in age. In children also, this GFR is less. Then food intake. Intake of food rich in proteins increases glomerular filtration rate. Regulation of glomerular filtration rate. It involves neural mechanism, hormonal mechanism, myogenic mechanism, and tubuloglomerular feedback. In neural mechanism, the activation of sympathetic fibers causes constriction of afferent arterioles, and it reduces the renal blood flow, thereby decreasing glomerular filtration rate. So, sympathetic stimulation, which occurs in emotion, fear, pain, etc., will cause reduction in glomerular filtration rate. In hormonal mechanism, we have discussed the role of hormones like angiotensins, dopamines, noradrenaline, etc. We have explained earlier. Then myogenic mechanism. When the arterial pressure increases, the afferent arteriole will be stretched, and this stretch induces contraction of the smooth muscles of afferent arteriole, thereby decreasing the filtration rate. And in hypotension, that is in reduced arterial pressure, the opposite mechanism functions. So this is the myogenic theory. That is, this myogenic mechanism controls the renal blood flow and glomerular filtration rate. Next is tubular glomerular feedback, and we have discussed it earlier. And this myogenic mechanism and tubular glomerular feedback, these two are the auto-regulation of glomerular filtration rate. Similar to the auto-regulation of renal blood flow, glomerular filtration rate is also auto-regulated, and this is due to the myogenic theory and theory of tubular-glomerular feedback. That's all about glomerular filtration, the first stage in urine formation. So thank you all. Hope for a better tomorrow. Remember, every dark cloud has a silver lining. So stay positive, work hard, and make it happen. Thank you guys.